The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let us start. So let me again start by reminding you what we did before. So consider, say we have a scalar field in ADS. So let me just summarize what we did before. So consider, say, a scalar field phi in ADS, and with mass m square, so with mass square given by m square, then we know when you go to the boundary of ADS, so let's take z goes to 0, then phi will have this, the following asymptotic behavior. So these are the two independent modes for phi near infinity. Of course, there are higher order corrections in Z. And this delta is given by 1/2 d plus nu, and nu is given by d squared divided by 4 plus m squared r squared. Okay. So this is the behavior. And so this phi is assumed to be dual to some boundary scalar operator. And then all those quantities on the gravity side, they all have counterpart on the field theory side. For example, the delta, which essentially is a function of mass, then essentially is the scaling dimension of O. It's a scaling dimension of O. And this AX essentially translates into the source for phi, or you can consider the momentum space version. Say you can do a Fourier transform, the AK, then go to the phi k. Okay? And then we also showed last time that the 2 nu times Bx is actually related to the expectation value of O. Okay? And again, there's a momentum space version of it. So you can just Fourier transform, then become OK and BK. Okay? So, and in particular, in the example, so we consider a scalar field example. In particular, in the example we considered, so we derived this relation from a free scalar field. But you can actually show this relation actually is generally true at nonlinear level. So if you also include higher orders, etc., so including the nonlinear dependence on phi, actually this relation remains true. But due to the time reason, we will not go into that. The proof is actually not very difficult. Anyway, so we consider the free scalar example. So in the example, we considered actually the B. So in momentum space, the B is actually proportional to A. Okay? Proportional to A, if you remember what we did last time. So in other words, this one-point function, so B is related to one-point function. So in other words, the one-point function is proportional to the source. So this is the standard story that the for the say OX equal to 0 when phi equal to 0. Okay, so if you don't have the source, then this 1-point function is 0. It's actually, say you don't have spontaneous expectation value for the O. And now, the fact that B proportional to A, so this is just reflect that in the presence of the source, then of course the expectation value, yeah, so let me write it in momentum space for simplicity, then will no longer vanishes, then will be say if you say this is assume the source is small, then you can expand the expectation value in power series of phi. So to the 0th order would be phi, and then phi square, etc. Okay. So at the linearized level, say we just find OK is proportional to phi k. Okay. We just find OK is proportional to phi k. And the proportional constant is in fact the 2-point function. Okay, it's in fact the 2-point function. So at linear level, so OK would be just proportional to phi k, but the proportional constant is just a 2-point function. So the reason is very simple. Yeah, so first let me write down the definition of this 2-point function. So Gex in coordinate space is defined to be, say, Ox or 0 because of translation symmetry. So you only need to, so I can put the other point to be 0. So this is only the function of one variable x. And then you can Fourier transform, then you get GEK. Okay? So this is how we define the GEK. And the GEK, so to see that this is true, you need to remember that the GEK is given from taking the generating functional delta phi k and delta phi minus k. Okay, then you set phi equal to 0. Okay, so this is the definition of the 2-point function. And then let's consider the one derivative on phi minus k. So one derivative on phi, so you can see that this takes one derivative on phi minus k. That just gives you the 1-point function in the presence of phi, and then delta phi k. Okay, then take phi equal to 0. Okay, so I just evaluated this derivative. So if you take this generating functional, take one derivative, you just get 1-point function, and then this is the other point function. Okay. Then at the linear level, so if OK is linear in phi k, of course taking derivative is just the same as dividing it. So this is the same. So continue over. This is same just as the phi k divided by phi k. Okay, at the linearized level. And so this tells you that this prefactor is just the 2-point function. Okay? The prefactor is just the 2-point function. And so we can now write the a 2-point function explicitly in terms of B and A. So this is just given by, because this is 2 nu BK. So this is just given by that. So this is just a quick summary of what we did at the end of last lecture. Yeah, so that's how you can find the 2-point function. So you work out what B is, what A is, and then the ratio of them is the 2-point function. And the way we work out the B and A is the following. So at the linearized level, when you solve the equation motion for phi, then you impose the boundary conditions at infinity if A should be equal to phi. But then there's another condition you impose to make sure the phi is actually regular in the interior. So that the regularity condition will lead to a relation between A and B. Okay? And so and then that will lead to the this 2-point function. Okay? Any questions on this? Is everything clear? Good. Okay, so now let's consider the higher point functions. So this is in principle straightforward to do, because recall that the log CFT phi, this generating functional on the right hand in the field theory, is just given by the classical action on the gravity side, with the boundary condition given by phi. Say you solve in the classical equation motions the on-shell action. Then the only thing you do, then you just, as what we did earlier, you just solve the equation motion for phi to the nonlinear order, and then evaluate the on-shell action, and then you just then you can express, for example, this SE in power series of phi, and then the coefficient of those. Then the coefficient for the power series of phi of this phi, then just give you the correlation functions. Okay, so in principle, this is straightforward to do. We know how to solve the classical equation motion. We know how to plug back into the action. Then you are done. Okay, so just to be a little bit more specific, so let's consider example. Say let's just consider two example. So again, let me just consider scalar fields. So now I add a linear term. Okay, add the linear term. Yeah, just for illustration, let me give you a toy example. And so one important thing is that in our setup, the lambda, this cubic coefficient, is proportional to kappa. And then if you translate into the field theory side, this is 1/n. Okay? So remember, for anything in the gravity action, you always have 1/kappa square, 1/g Newton before the overall action. And then when we try to change phi into canonical normalized, and then you rescale phi, and the consequence is that those cubic term or quartic term, then they will have coefficient proportional to kappa. Okay, and according to this rule, if you have a quartic term, then that will be proportional to kappa square, etc. And so the key is that as far as phi is order 1, then you can actually treat those higher order terms by perturbation, because the coefficient is small. Okay, the coefficient is small. Okay, and of course you can also consider the situation which phi is large, then you have to solve the full nonlinear problem. Then you cannot do the perturbative expansion, then you have to do the problem. Anyway, so for our purpose, if you want to find the higher point function for phi, then you need to solve this equation. So box phi is just a Laplace operator. So I just save time. And so you need to solve this equation. And with the boundary condition, still the boundary condition, the boundary value of capital phi is equal to this phi x. Okay? So let me call this equation star. So as I said, because this lambda is small, so you can actually carry out, you can try to solve this equation just perturbatively in lambda. And essentially, you are solving it perturbatively in this phi, because everything in the end will be expressed in this phi. Okay. So so one can solve star perturbatively in phi, which is the boundary value of the field. And so say phi c, you can expand it as phi 1 plus phi 2, etc. So the classical solution expanded, and this is linear in phi, say. And this is quadratic in phi. And etc. Okay? And then when you plug in back this into the action, then you find the on-shell action can also expand it in power series of this phi. So you will have S2 phi start with quadratic order, S3 phi, etc. Okay? And then the coefficient here give you the 2-point function. And then coefficient here give you the 3-point function. And the coefficient here give you a 4-point function, etc. Okay? So I hope the procedure is clear. Any questions regarding this? So even though this is very straightforward to do conceptually, but in practice that's not what we would do, because this is very tedious. It's very tedious. And our knowledge of quantum field theory gives us something much simpler to deal with. Because this essentially, if you think about it, is not very different from doing correlation function calculation just in the flat space quantum field theory. And there, when you calculate the Green function in flat space, in flat space quantum field theory, what do you do? Do you try to solve the classical equation of motion and you iterate the equation? What do you do? Yeah, you use Feynman diagrams. So here is exactly the same thing. Okay? So here, it's much easier. You just do the Feynman diagrams. So let me first remind you what we do in the flat space. Okay? So recall. So let's now go to the field theory 1. Standard ordinary flat space QFT. Okay? So now let's consider the lambda phi cube theory in flat space. Okay? Just the same theory. Now it's in the flat space. Okay? Yeah, let me call this star star. So essentially, let's just consider star star in flat space. Now, in flat Euclidean space. Okay. Let's just consider it in flat Euclidean space. So if we are given a field theory like that, so how would you calculate the following correlation function? Say, suppose I want to calculate phi x1, phi xn. So now this x1, xn, they're just flat space coordinates. Okay? Yeah, let me just, to distinguish them, let me just call y1, yn, just not to confuse about our ADS coordinates. So in flat space with the y mu. Okay? In flat space with coordinate y mu. So now suppose you want to calculate the correlation function for this. Okay, what do you do? So what do? It's easy. What you do is that this series have a propagator G. This have a propagator, and also this series have a interaction vertex which is controlled by lambda. And then when you calculate such endpoint functions, you just fix your endpoint. So now remember, this is slightly different than what we normally do in field theory 1, because here we're doing coordinate space rather than in momentum space. In field theory 1, you're more used to doing in momentum space. So here what you do is that you fix y1, y2, y3, essentially yn. So this is essentially the location of your insertion, of your field insertion. So essentially imagine there's a source there. And then you just connect all of the external points by propagators and with this kind of interaction vortices. Okay? So for example, you can have something like this. Etc. Okay? And I say this connect to some boundary point, some other point, etc. Say y is 5. And this also have lines. Anyway, you just draw all possible diagrams, and you calculate that diagram. You calculate those diagrams, and that give you this thing. And essentially, the diagrams automatically give you the iteration procedure. Okay. So now back to ADS. Essentially, we can just do exactly the same thing. So back to ADS. Just remind yourself of the procedure of calculating this and what we are going to do here, and you easily convince yourself. So it requires a couple of minutes thinking, but that I will leave it to yourself. That actually that procedure is no different from just doing the calculation like this. So one major difference, of course, there's a difference is that now we are in the curved space-time rather than flat space-time. But there's another major difference is that the source so here the source all lies in the interior of your space-time where you insert the operator. But here, all the source phi x, they lie at the boundary. Okay? That's essentially the only difference. So if I just schematically, then this is ADS, this is the boundary. Then essentially all the points lying on the boundary, so we have x1, say x2. So let's consider 4-point function. So you have, because each one of them is labeled by the boundary point. And then for the 4-point function, you just connect. Say you can connect the diagram like this. Okay, so again, you have the vertices, which is the lambda cube vertices, but your endpoint is all lying on the boundary. So this structure also tells you actually there's two types of propagators. Because there one type of propagator connect the two Bach points, and then there's this kind of propagator which connect the Bach point to the boundary points. Okay? So this is the difference, one major difference from the flat space case. So here all the propagators are the same. Okay? So here the difference is now you can only have, you also have propagators which come from boundary to the Bach. So in this case there are two kinds of propagators. So here you have two types of propagators. Okay. So one type of propagator is what we call the Bach-to-Bach propagator. Somehow this is going up and up. Okay, then I lost some blackboard space. So this is the complete analog. This is the precise counterpart of the flat space propagator. So this connects 2 points, Zx, Z prime, X prime. So I still use the notation that Z is the Bach radial direction and X is along the boundary direction. And this Bach-to-Bach propagator satisfies the standard Laplace equation, just as in flat space. So this gives you the delta function. Yeah, so let me just write it explicit. Z minus Z prime delta X minus X prime. Okay, so this is a complete analog of the standard flat space propagator. Just now we are in anti-de Sitter space. Okay, so counterpart. So this is a counterpart in ADS standard flat space propagator. Okay. So in particular, so as a propagator, this should be normalizable. Should be normalizable. In either Z or Z prime, okay? So when you take them to the boundary, okay? So more explicitly, for example, the Z, X Z prime, X prime should scale as Z prime to the power delta when you take Z prime go to 0. Okay? And of course, this should also be regular. You should not have singularities as Z goes infinity. Okay, they should also be regular. So essentially, these conditions will precisely define those propagators. But in ADS, we also, because the source lies on the boundary, because of this boundary condition, so we also have so-called boundary-to-Bach propagators. So the boundary-to-Bach propagators So this propagator is just as the standard in flat space 1, it propagates the field from one point to the other point. So that's why there's a delta function here. So the standard story, there's a delta function here, and you propagate the field starting from this point to some from this point to that point. Okay, so this boundary to Markov propagator normally is written as kz x, but the second index only have x prime, because this is when you take the boundary point to a bot point. A boundary point, of course, there's no z anymore. So z prime is 0 here. So you don't need to write it. Okay? And this boundary to Markov propagator should satisfy the Laplace equation. But now the key point is that on the right-hand side, because there's no Bach source, so the right-hand side should be 0 rather than the delta function. So that delta function is due to the Bach source. But we have to make sure this k have the right non-normalizable boundary conditions. So it has the right boundary condition to the boundary. So this when approach to the boundary, as z goes to 0, should be like z d delta x minus x prime. Okay? So this is for the purpose. So the k satisfies the Laplace equation without a source. But when you take this propagator to the boundary, and then it should give you the non-normalizable the boundary conditions, because it should approach a source. And the delta function is put here so that, say, if you write, say, a Bach field, which is sourced by some boundary source, say kz x prime times phi x prime, and this will have right boundary condition that the phi xz goes to z d minus delta phi x. Okay, as z goes to 0. Okay? So this boundary to Bach propagator does not have a source in the Bach, but does have a source in the boundary. Okay, non-normalizable for off in the boundary. So now with these two propagator, then the story just exactly as in the standard way you obtain the Green functions. Okay, it just really no difference. It just really no difference. So let me just summarize what we have discussed. Summarize. That the boundary endpoint function, okay, can be obtained by essentially endpoint function of the phi field in the gravity side write it here, just related to the endpoint function of the gravity field on the gravity side with all these points x1, xn, they are lying on the boundary, okay? So you just essentially compute on the ADS side, treat it as ordinary field theory, then compute this endpoint function of your fields, but just put the fields on the boundary, okay? Put the field on the boundary. And then that will just give you the ADS correlation functions. Yeah, and then you just need to distinguish two types of propagators, Bach-to-Bach propagator and Bach-to-boundary propagator. So any questions regarding this?
Now here the K goes to D to the D minus delta, but there the G goes to D pi to the delta.
Yeah.
So why are they different?
Oh, it's because this must have a source. So the boundary to Bach propagator corresponding to you propagate a source from the boundary to the Bach. So that means that field must have the right boundary condition. Must have the right boundary condition. So that's the reason for this. You must have non-normalizable boundary conditions. And that propagator is just the standard flat space propagator. Of course, it's always normalizable. And in the flat space, when you construct the propagators, of course, it's always using the normalizable wave function.
Okay, so this is not normalized.
No, this is not normalizable. This is designed so that you have the right boundary condition. Yeah. So this is designed so that you can propagate just as in flat space. If you have phi at this point, and then you can propagate to the other point by convolution. And of course, when you write down a Bach field phi in general, you do it only construct them out of the normalizable modes. Okay. Any questions? Good. Okay, so now let me make some remarks. Okay. So here, this procedure of iterating the classical equation motion, solving the classical equation motion and then iterating in the action. Of course, again, from our experience with quantum field theory, that only give you the tree-level diagrams. Okay, they only give you the tree-level diagrams. Say if I really write the Bach path integral, so ZCFT phi, then in the semi-classical limit, it can be written as Z gravity, which is phi with the right boundary condition. And then on the gravity side, at semi-classical level, we can actually write down the path integral for this gravity partition function. Okay, so that's what we discussed before. And then at the leading order, in performing this path integral, so the leading order performing this path integral, of course, you just get what we have been doing so far. You just evaluate it at the classical solutions. Okay? But in principle, you can also consider fluctuations. So this is fluctuations around, say, the classical solution phi c. And then the action for the fluctuations is just given by phi c plus phi, the minus, of course, the classical action. So you just expand around the phi c, okay? So when you expand this to leading order will be quadratic in small phi, or I should not call it small phi. Maybe let me call it chi, because that is the same as that phi. So this chi is a small fluctuations around the phi c. And so if you expand this in chi, the linear order is 0 because the phi c satisfies equation motion. So this will start quadratic order, and then cubic order, etc. So evaluate the quadratic order is a Gaussian, and then that's the one loop diagram. And then if you go to higher orders, and then give you higher order diagrams. So if you now include the fluctuations, so SEC, so the SE phi c which is a classical action. This is encodes only tree-level diagrams. Tree diagrams. And when you include the fluctuations phi, the fluctuation is chi, and then this corresponding to include loops. Okay. So again, the whole procedure can be captured by the Feynman diagrams, and so the advantage of the Feynman diagram is actually there's a natural generalization to the loop diagrams, and then you just include the loops here. Okay, just include the loops here. Yeah. Okay, for example, here you can have something like this. You can also have something like this. Okay. So that's corresponding to including the fluctuations around the saddle point, including the fluctuations around the saddle point. Any questions regarding this point? Good. Yes.
So when people draw these like so-called Witten diagrams, I mean, where they draw up like this circle,
Right.
Is that basically what we're doing?
Yeah, right. Yeah, so let me just explain one thing. So in the Euclidean, so I have been drawing the ideas like this. So this is equal to 0, etc. So when you go to Euclidean signature, so as you will do in your P set, then this z equal to infinity is actually, you can argue exactly a single point. Even though, yeah, so let me just write down the metric. So the metric is R squared, E squared. So when you go to Euclidean signature, you just have dx squared. So this is a full Euclidean metric. So there's something interesting about the difference between the Euclidean and Lorentzian, even though from this picture is roughly the same. So z equal to 0, you go to z notch. And in the Euclidean case, you can actually show that z equal to infinity, even though naively z equal to infinity, you still have a full Euclidean plane. But you can argue actually the whole thing is actually a point. And you can roughly see it as follows: when you go to z equal to infinity, and then overall factor goes to 0. So essentially, the whole space shrink to 0, shrink to a point. Okay, the whole space shrink to a point. So in the Euclidean, so z equal to infinity is essentially a point. And then topologically, then this is equivalent to have a disk. To have a disk. Topologically, the whole space is just have a disk, and the z equal to infinity is one point on the boundary, and the other is z equal to 0 anyway, and so this is the interior of the space. Okay. Yes.
So in other words, so the entire perimeter of the circle is like that. It's
this is the boundary. Yeah, now this is the boundary. Yeah, essentially you can imagine at each point here is r to the power r to the d. Then you add a point at the infinity, then become a sphere. Yeah, it becomes a sphere, and then the whole thing becomes like a disk. Yeah. Okay. Yeah. So this is the yeah. So normally then people will draw that. So topologically in Euclidean ideas it's like this. Then people will just draw diagrams like this. Draw diagrams like this. Okay.
You add a single point to the boundary, a single point which is equal to infinity to the boundary, which is z equal to 0.
Sorry?
You mean that you add the point z equal to infinity?
Yeah. This point turns out you can actually lie on the boundary.
But then on the boundary, the value of t is not continuous.
Yeah, this is related to the. so this is due to the coordinate choice. It's just this coordinate becomes singular at that point. You can rewrite the. Yeah, the simplest thing is that you rewrite these Poincare coordinates to the coordinate which is that parameterize the boundary really as a sphere, and then you will see, because when you write the sphere as a plane, and then there's one point becomes singular. Yeah, this is just a standard story. Yeah, just that coordinate choice is singular. Any other questions? Good. Okay, so this is the first remark. The second remark is that, so this is a little bit unusual correlation function. So this is a Bach correlation functions, but with all points lying in the boundary. So the standard analog, so the complete analog, so the counterpart, or just the exact analog of standard flat space correlation functions in ADS are, say, you just consider n Bach point just consider n Bach points and look at these correlation functions. Okay. So this then will be really just like when you do the standard QFT1 correlation functions. Then you have n points, z1, x1, all in the Bach, z2, x2, etc. And then you just draw diagram between them, etc. Okay. And then the array propagator here would be just Bach to Bach propagator. There's no boundary to Bach propagator. Okay, there's no boundary to Bach propagator. Just all is Bach to Bach propagator. So this is a complete analog of your ordinary flat space green functions. But you can easily imagine that this correlation function must be related to those correlation functions if you just take those points to the boundary. Okay, you can just take those points to the boundary. So naturally expect say those correlation functions which things are at the boundary must be related to those kind of standard correlation functions which you take the point to the boundary. Okay. So those must be somehow in the end must be the same. So if I take those points to the boundary, I should recover that guy. Okay? So indeed, this relation is true. And you will work it out yourself in the P set. Once you load the, you see the only difference is the following. When you take those points to the boundary, what you get is the boundary limit. So now let's imagine you take those points to the boundary. Because here is all Bach propagator. So those propagator which connect to the boundary would be the boundary limit of the Bach propagator, okay? And then it just boils down to what is the relation between the boundary limit of the Bach propagator and this boundary to the Bach propagator, okay? So it just boils down. So the relation. So the above relation. Yeah, let me just better just call it a number. So this star just boils down to the relation between the k, z, x, x prime, which is our boundary to Bach propagator, and limit z prime goes to 0, g x z x prime z prime. Okay. So you will find that these two guys are proportional to each other, and once you extract out that proportional factor, and then you just relate them. Okay. So this is just another way to calculate. Yeah, because this is the boundary correlation functions. So this is the boundary correlation functions. So this is related to the CFT correlation functions, and then you can also calculate the CFT correlation function just by taking the limits of the Bach correlation functions. Okay. So this you will work out a little bit. Yeah, you will work out the precise relation in your P set if you not have. Yeah, maybe some of you have looked at it already. So any questions on this?
What is the advantage of introducing another to explicit?
Yeah, just different ways of calculating things, and of course the normally have many different ways to calculate things. Some of them may be convenient this way, some of them may be convenient for that purpose, etc. It depends. Yeah. So normally we just directly using the Bach to a boundary propagator. If you just do the calculation, the Bach to boundary propagator actually is simpler. And but sometimes for certain conceptual questions, actually this actually becomes simpler. This becomes simpler. Yeah. So now let's look at Wilson loops. Okay. So how do you calculate the Wilson loops using gravity? So in the gauge theory, so I assume you have already done the QFT2 in the gauge theory in QFT2. Yeah. So in the gauge theory, the Wilson loop is essentially one of the most important observables. Okay. The Wilson loop is normally defined in the following way. Okay, so now I will explain my notation. So let me also add a subscript r here. So first, so C is a closed path. So this is defined for closed path. Okay. And A mu is a matrix. So we consider long-abelian gauge theory. So A mu is a matrix. Writing the standard way in terms of the generator in some representations R. Okay. So this is in some representations. So this is just the generators of the gauge group in some representation, which you call R. And then P P is the path ordering. Okay, P is the path ordering. So in general, you can choose any representations you want, but often we choose R, say, in fundamental representation. For example, that's normally what we do in QCD in fundamental representation. But you can choose R to be in any representation. Okay? So the physical meaning of this phase factor, so this operator by definition is gauge invariant because of this trace. And you need the path ordering because you have a matrix here. And the matrix at different points, they don't commute. So you need to specify ordering. And so you just specify it by the order of the path. Okay? And so the physical meaning of the Wilson loop so this is essentially the phase factor associated with transporting an external particle in a given representation, say in R representation, along C. Okay? So you transport the particle along some path, and you come back to the same point. Then you find that phase not necessarily go back to 0. And so this non-trivial phase essentially tells you there's a non-trivial gauge field there. And so this is the, so this provides the probe of the gauge fields. Okay? Yes?
I know that people talk about, I know that it's somehow unobservable, but is it actually observable? Like, can you actually do an experiment to measure this phase?
I don't think so. Not, I think in the you can, you can. It depends. It depends. In some situations, in some situations you can. It's something in principle. Yeah, let me mention something else. Then the answer to this question will be seen. Okay, so the simplest case would be the WC, just the single point function of WC, say in the vacuum. So this is the simplest observables. But of course, you can also consider the generic, say large number of several loops in some general state, say for example finite temperature, etc. Okay. So so you can so these are the typical observables. So now let me emphasize this external. So this external is very important. So normally, by calling something external, is that we mean that this particle have an infinite mass, just is infinite heavy. And the reason we want it to be infinite heavy, because if you have because only for infinite heavy particle, in principle, you can localize the longer path. Okay, then you can make mathematical sense that the precise path. Otherwise, if it's a fluctuating particle, then you cannot specify a path, ambiguously. Anyway, so when we say an external particle, I always say a particle which is assumed to be infinitely massive. Okay. And also, I will introduce terminology when this R is in the fundamental representation. Yeah, maybe not right here, but when this R is in the fundamental representation, I will call the corresponding particle a quark. Okay. And if it's in the fundamental representation, I will call it a quark. So I will often just consider the fundamental representation. So we will considering then the phase factor will correspond to U transport the quark. Okay? So one of the very often used loop is a rectangular loop. So this is along some spatial direction, so this is the time direction. So let's say the spatial direction is L with L, and the time direction is the length is T. So imagine you have a loop like this. Okay? So to read in order, so normally we consider the t, say the length of the loop in the time direction much greater than the L. Okay? So in such a limit, then essentially you can ignore the contribution from this side, from these two short sides. So in the limit which this t goes to infinity, okay, you can just to lead in order, you can ignore the short side, and then you can think of this loop. Then I just has a particle. So this is a particle moving forward in time. This is a particle moving backward in time. Then you can consider this as a particle and the antiparticle moving forward in time. Okay. And then so in this case, you can argue on general ground. Then this will just, to leading order, will give you something IET. And this E, it just can be interpreted as a potential energy between an external quark and the anti-quark. Okay. So at least in this example, this is the sense I said. You may, in this case, you may be able to measure this Wilson loop, because if you can measure, say experimentally, you may be able to measure this energy between the two particles, and you can measure the energy between the two particles, and then essentially you can say I have measured the loop, and then you can compare with the prediction of the loop. Okay, so again, in order to make this interpretation make sense, this particle have infinite energy is very important. Okay, and again, only for the precise, only for the very heavy particle, you can really localize them and then talk about the potential energy between these two particles. Okay, and otherwise, if they fluctuate a lot, then it's hard to make it precise. So now the question is, how do we calculate this quantity in ADS? Okay. So now it's how do we calculate this quantity in ADS? So I will, when I don't put the index here, I just means that this is in the fundamental representation, okay? Okay. Question how we do that. So in order to answer this question, we first need to understand how to introduce a fundamental external particle, external quark, in an equal super Yang-Mills series. Okay? So how to introduce a fundamental external quark in an equal super Yang-Mills series? So we know, as we discussed before, that everything in the equal super Yang-Mills series, say all the fundamental fields, all the fields in the equal super Yang-Mills series, they are in the joint representation. There's nothing in the fundamental representation. Okay, and everything is in the joint representation. So first we need to introduce a fundamental object, an object we transform on the fundamental representation. Then we need to, after we have done that, then we need to translate that quantity to the gravity side. Okay, and then we understand the gravity description. Description of such an external particle. So this is easy to do. This is easy to do. So let's first think about how to do this in the equal for Yang-Mills series. And this is very intuitive by using this D-brane picture. So we know that the D3-brane, the equal super Yang-Mills series, come from the Lagrange series of n D3-branes. Okay, come from the Lagrange series of n D3-branes. So how do we introduce an external particle? So now let's imagine, consider n plus 1 of them. Okay, consider n plus 1 of them. And then we separate one from the rest. So this is still n. Separate one from the rest. Okay? So then there can be open string connect between them. So suppose I separate by some distance r in the transverse direction to the D3-brane. Okay? So as we described before, this breaks, such a separation breaks the SUN plus 1 symmetry of the ND3-brane into SUN, and then the single U1 of this one brane. Okay? Okay. In particular, such an open string, the endpoint. So let's look at the endpoint. Then the endpoint of this string can only have n indices. Okay? Yeah, because this is a single string. One end ending on the other side, there's only one index. And here, they can only have n possible index. So such a fundamental string transform transform in the fundamental representation. Okay? SUN. And this also have a so from the point of view of this SUN gauge theory, this is a quark. So this endpoint is a quark. So this is a quark. This is a quark. And the mass of this quark is equal to, so let me call the mass capital M. So the mass of this quark is equal to R, the length of the between them, divided by the tension of the string. So this we have derived before. Okay? So this just gives you the mass of the quark. So when you separate one d brane from the other, so you have introduced this quark with a mass. Okay? So now let's consider this no-energy limit of Marder-Sinner. So in the low-energy limit of Marder-Sinner, so we want to keep this quark, okay? So that corresponding to, we want to take alpha prime go to 0, okay? But we want to keep this quark in the low energy spectrum because we want this remain in the incompatible super Yang-Mills series because we want to introduce this particle. So in this low energy limit, when we take alpha prime go to 0 limit, we also want to take at the same time r goes to 0 limit so that this mass term r divided by alpha prime remain finite. Okay? Then that means this will remain, this particle, such kind of fundamental representation will remain in the incompatible super Yang-Mills series. Okay? Because other modes are massive, and then when alpha prime goes to 0 limit, they go to infinity, and those modes will remain with the incompatible super Yang-Mills series. So now let's see what happens this on the gravity side. Okay? So here you will need to fill in some details yourself. Okay? You will fill in some details yourself. I only tell you the answer. So on the gravity side, you have this ND3 brane, then you have one brane which are separated from this ND3 brane, and their separation is such that when you take alpha prime go to 0 limit, their ratio is finite. Okay? So now in the gravity limit, now in the gravity side, you have to take this so-called Leo horizon limit with this taking this into account. Okay? So what do you find in the gravity side is that, as before, that ND3 brane now disappeared into r equal to 0, which is, remember, r equal to 0 is at the infinite proper distance away. And now we are using this r coordinate now, okay? And when we take this lower limit, we're using this r coordinate rather than this z coordinate. So in that case, you have r equal to infinity. Then the brane essentially goes to r equal to 0, which has infinite proper distance away from any point, from any finite r. Okay? So now this is an exercise for yourself. Just to repeat our previously argument. Then you will find that in this regime, when you take alpha prime go to 0, this r finite, this D3 brane does not disappear. This single D3 brane will remain in the ADS. So the difference from our previous story is that in addition to the ADS, now you have additional D3 brane at some point in S5. Okay? Yeah, because D3 brane is in some transverse directions, which now become S5. So you have a D3 brane which is parallel to the boundary coordinates, but sitting at one point in the S5. Okay? And I think this picture is reasonable, but you should check yourself. Just in this regime, this rebrand does not go away. Okay? And another remarkable thing you will check yourself is that when you take the decoupled limit, now in this picture, this is a flat space. Okay, this is flat space. And then you have this formula. And now when you take this decoupled limit, this now becomes ADS. Now this is ADS at some radius r. Okay, at some radius r, controlled by this r. And now you can check one nice thing. Check one nice thing. Is that in ADS, if you consider a string, straight string from this D3 brane all the way to r equal to 0, which is this string have exactly the same mass. Okay? So this string, so the mass is equal to r divided by 2 power of prime, also in ADS5 times S5, in ADS5. Okay? So this is a consistency check. So this is a consistent check, because when you take the low energy limits, of course, you should not change the mass of the mass of the string will not change here. The only question is whether they will stay in the spectrum or not stay in the low energy spectrum. Okay, the mass will not change, and you will see that when you take that limit, you find this D3 brane remains here, and this string, which now will be connect some r to r equal to 0, which is now just some ADS. This is just some interior of ADS infinite proper distance away, and then you can check that in the ADS metric, the energy of this brane viewed from the boundary series, viewed from the boundary time. Okay, you have to this redshift factor, etc., remains exactly equal to this. Okay, so this is an important self-consistency check, which I will not do it here. So now the story becomes simple. So now we find we generate such a string with such a fundamental particle with such a mass. But in order to introduce an external particle, in order to have external particle, we need to take a mass to go to infinity. So that means we need to take r go to infinity. So that means we want this rebrand to lie on the boundary of ADS. Okay? So to summarize, so now we want to move this rebrand. In order for external particle, we want to take m go to infinity, then we want to take this r go to infinity. So we want this rebrand to actually lie on the boundary of ADS. So let us just conclude, summarize. An external quark with infinite mass in an equal to 4 Yang-Mills series is described by a string ending on the boundary of ADS. So this is r equal to infinity. Okay? Because now we have put in this rebrand to the boundary, and then we're corresponding to a string ending on the boundary of ADS. External quark with m infinity in ADS corresponding to a string ending at boundary ADS. And in particular, the location of the string can be mapped to the location of the quark. Okay? So the endpoint of the string is the location of the quark. So now we have found a very nice picture. is that introduce a fundamental quark in any super Yang-Mills series corresponding to introduce such a string. Okay? And now when you do a Wilson loop, then corresponding to transport this string around some path, the end point of the string around some path in the field series. Okay? Okay, so I will stop here.